We're surrounded every day with physical materials, whether that's clothing or buildings or products or cars or planes. They're all made out of materials, and there's definitely a goal to make them smarter and smarter and smarter. But today, the only way to make something smarter, we think, is to make it more robotic or more like a computer. You don't want to make something smarter and make it more expensive or more complex. You want to make something smarter that's more and more simple. So our principle is that we want to program materials to become smarter. I'm Skylar Tibbits, and I co-direct the Self-Assembly Lab at MIT in the Department of Architecture. So at the Self-Assembly Lab, we have three main topics of research. The first one is self-assembly, and that's where individual components come together on their own without humans or machines. The second one is programmable materials, and the idea is you want to program a material to change shape or change property. And the third research topic is phase change, so how materials go from solid to liquid and liquid to solid. Self-assembly is really useful because we spend a lot of energy and time putting things together. So there's three principles to self-assembly. The first is geometry, the second is energy, and the third is how they connect. So in terms of geometry, if you change the shape or the geometric structure of the material, it'll produce different effects. You'll make a dodecahedron versus a chair versus a cell phone, for example. If you change the connections, that allows things to stick or not stick. You want these things to come together and stick in just the right places, but you need a principle called error correction where parts can connect, but if they're wrong, they should disconnect, and only when they're right do they stay connected. And then the third one is energy, and you need to somehow shake them around, tumble them. You can do it in different environments, like underwater with pumps or with fans or like tumbling, shaking. You need some type of energy to get them all excited, find one another, connect in just the right places with just the right geometry, and then they'll assemble precise structures. One thing that we're working on are programmable materials, and this started with our work on 4D printing. And the idea is that you multi-material print structures so that you can then activate them, in this case based on water. When you dip it in water, then this flat sheet turns into a truncated octahedron. Another aspect of our research is on phase change, so how to go from liquid to solid and solid to liquid. And that allows us to change the properties of a material to make it stiff or flexible, to make it expand or contract. So you can make things like reversible packaging or reversible concrete or new crash protection. All of these are based on the expansion and contraction of a material or how flexible or stiff a material is. I think the impact of our research is really going to be in new modes of construction manufacturing, new product materials and performance, new ways to think about materials. And in some ways, it's like blending the digital world and our understanding of computation with the physical world and our understanding of materials. Some of our work is already out there, so we've done some research around orthodontics and medical devices that are already in clinical trials, and we've done some research with Airbus on a new component for their engine. So some of these devices and research technologies have led to real applications. I wouldn't say that it's really widespread at this point, but we're optimistic that there's a lot of new technologies and new capabilities that are coming on, and hopefully we'll see something in the coming years that'll be much more widespread and kind of mass market.